trapped. We all are. And the bars of our prison aren't made of steel. They're woven from the laws of physics themselves. Every human who will ever live is locked inside a cage. The stars aren't destinations, they're taunts. And here is a question. If you could break one law of physics for a day, which would it be? And what would you do? Let me know in the comments. I will pin the most creative answer. Now let's begin. Our solar system, vast as it seems, is tiny compared to interstellar distances. Neptune, the outermost planet, orbits about 2.8 billion miles from the Sun. Voyager 1, which has left the solar system, is currently about 14.5 billion miles from Earth. These are incomprehensible distances by human standards. Yet Proxima Centauri is more than 1,700 times farther away than Voyager 1 is right now. 1,700 times. The gap between planetary exploration and interstellar exploration isn't a gap, it's an abyss. And Proxima Centauri, I cannot stress this enough, is our nearest neighbor. The star after that is about 6 light-years away, then 8.6, then 10.5. The distances grow like compound interest. Most of the stars you can see with your naked eye are dozens, hundreds, even thousands of light-years distant. The center of our Milky Way galaxy is roughly 26,000 light-years from Earth, and there are other galaxies beyond ours, millions and billions of light-years away. Andromeda, our nearest large galactic neighbor, is 2.5 million light-years distant. Even if we could somehow travel at the speed of light itself, which we cannot, it would take 2.5 million years to get there. This is where the dream crashes against the wall of physical law. The universe has set these rules and they are absolute. You can't negotiate with physics, you can't find a loophole in the structure of space-time. The speed of light isn't just fast, it's the fastest anything can go, and it's still not nearly fast enough to make the universe accessible to us within human timescales. So when I say we will never travel among the stars, I'm not being pessimistic. I'm acknowledging what the math tells us, what the physics demands. We are an intelligent species on a small world, looking out at a universe so vast that most of it will forever remain beyond our reach. Not beyond our sight, we can observe the cosmos through our telescopes, study it with our instruments, unravel its secrets with mathematics and physics. But physically going there, sending our bodies across interstellar space, building colonies on alien worlds, that dream might remain exactly what it is, a dream. But this isn't the end of the story. There are possibilities, however remote, there are ideas, however speculative, and there are questions we haven't fully answered yet. What if we could, somehow, approach the speed of light more closely? What if we discovered new physics that we don't currently understand? What if we accepted journeys lasting generations, sending colonists who would never see the destination but whose descendants would? And before you think I'm about to offer hope, let me warn you, each of these possibilities comes with its own devastating problems. Problems that might be even more insurmountable than the distance itself. Make sure you're subscribed to the channel because we're only getting started. Let's talk about something equally unforgiving: energy. Because even if we somehow accept the mind-bending distances between stars, we still face a problem that makes engineers and physicists shake their heads in frustration. Moving anything, even a tiny probe, to relativistic speeds requires energy on a scale that defies common sense. There's a famous equation in rocketry called the Tsiolkovsky rocket equation. It was developed by Russian scientist Konstantin Tsiolkovsky in 1897, and it describes the relationship between the velocity a rocket can achieve, its exhaust velocity, and the mass of fuel it needs to carry. The equation itself is elegant, but its implications are brutal. It tells us that for every additional increment of speed you want to achieve, you need exponentially more fuel. Not linearly more, exponentially more. Let's break this down with an example. Imagine you want to accelerate a spacecraft to 1% of the speed of light. That's about 1,800 miles per second. Sounds fast, right? But at that velocity, it would still take over 400 years to reach Proxima Centauri. Still, let's try. Using conventional chemical rockets, the kind we use today, to launch satellites and send probes to Mars, the mass ratio between your fuel and your payload would be astronomical. You would need a fuel tank so massive compared to your tiny spacecraft that it becomes absurd. We're talking about ratios that might require your fuel to outweigh your payload by factors of millions or even billions, and that's just to reach 1% of light speed. What if you wanted to go faster? 10% of light speed, 20%? The fuel requirements don't just double or triple, they explode. They grow so rapidly that you quickly reach a point where you'd need more fuel than exists in several planets. This is the tyranny of the rocket equation. The faster you want to go, the more fuel you need, but the more fuel you carry, the heavier your spacecraft becomes, which means you need even more fuel to accelerate that additional fuel. It's a vicious cycle with no escape. This is why the breakthrough Starshot concept uses light sails instead of rockets. By leaving the energy source behind on Earth in the form of powerful lasers, you eliminate the need to carry fuel. The spacecraft itself can be incredibly lightweight because it doesn't need propellant tanks or engines. But this creates a different problem. You can't slow down. Once you're accelerated to 20% light speed by that laser array, you're committed. You're going to scream past your destination at 37,000 miles per second with no way to brake. Imagine driving a car down a highway at hundreds of thousands of miles per hour with no brakes. You might see interesting things out the window as you pass them in a blur, but you're never stopping to take a closer look. Some scientists have proposed using the destination star's own light to slow down. The idea is that you flip your light sail around as you approach Proxima Centauri, and the star's radiation pressure gradually decelerates you. It's a beautiful idea in theory, but the numbers don't work out. Proxima Centauri is a red dwarf, meaning it's much dimmer than our Sun. The radiation pressure from such a faint star would be far too weak to provide meaningful deceleration in a reasonable time frame. You'd sail past the star before it could slow you down enough to matter. Nuclear propulsion has been proposed as an alternative. The idea dates back to projects like Orion in the 1950s and more recently Project Daedalus from the 1970s. These concepts involve using nuclear reactions to propel a spacecraft. Project Daedalus, designed by the British Interplanetary Society, envisioned a two-stage spacecraft powered by nuclear fusion reactions. The design was ambitious: detonate fusion pellets behind the spacecraft and use the expanding plasma to push you forward. The calculations suggested this could potentially reach 12% of light speed, which would get you to Proxima Centauri in about 36 years. But here's the problem. Building a spacecraft like Daedalus would require resources on an almost unimaginable scale. The initial mass would be around 54,000 tons, most of it fuel. We're talking about constructing something in space larger than a battleship, filled with fusion fuel, and somehow igniting controlled fusion reactions continuously for years. We haven't even achieved sustained controlled fusion for energy generation here on Earth yet, despite decades of research and billions of dollars invested. The ITER project, the international effort to demonstrate fusion power, won't be operational until the 2030s or 2040s, and that's just to show we can get more energy out than we put in, not to build a practical power plant, much less a spacecraft engine. And even if we solved fusion propulsion, we'd face the shielding problem again. At 12% light speed, the radiation from interstellar hydrogen becomes lethal. Any crew aboard such a vessel would need protection so substantial that it would add enormous mass to the spacecraft, potentially requiring even more fuel, bringing us back to that vicious cycle. So what about generation ships? This is the concept that science fiction loves. Massive vessels, essentially self-contained worlds traveling through space for centuries or millennia, carrying multiple generations of humans who would be born, live their entire lives, and die aboard the ship, never setting foot on Earth or the destination planet. Their descendants, many generations later, would finally arrive. It's a romantic notion, the idea of a self-sustaining human habitat crossing the gulf between stars. But when you examine the practical requirements, the romance fades quickly. Research conducted by scientists like Frédéric Marin at the University of Strasbourg has used Monte Carlo simulations to calculate the minimum viable population for such a journey. Their findings are sobering. For a journey to Proxima Centauri lasting several thousand years, you would need a starting population of at least 98 people to maintain genetic diversity and avoid the catastrophic effects of inbreeding. And that's assuming everything goes perfectly with no major accidents, no plagues, no social collapse, and carefully managed breeding programs to ensure genetic health. If you allow for any significant probability of disaster, you'd need to start with several hundred people, possibly more. Think about what that means. You're not launching a small crew, you're launching a small town, complete with everything needed to sustain human life for thousands of years. You'd need agriculture, recycling systems for air and water, manufacturing capabilities to produce tools and spare parts, medical facilities, educational systems, and some form of governance to prevent social breakdown over the centuries. The spacecraft would need to be enormous, possibly miles in length, rotating to provide artificial gravity. The structural requirements alone would demand materials and engineering far beyond our current capabilities. And here's a darker question that nobody likes to talk about. What happens to the generations born in the middle of that journey? The original crew members volunteered for this mission. They knew what they were signing up for. But what about their great-great-great-grandchildren? They never asked to be born on a spaceship. They never chose to spend their entire existence confined to a metal tube sailing through the void. What psychological effects would that have? What kind of society would develop in such isolation? There's also the problem of genetic degradation. Even with a starting population large enough to maintain diversity, cosmic radiation would constantly bombard the ship. High-energy particles, mostly protons and heavier atomic nuclei, stream through space continuously. Earth's magnetic field and atmosphere protect us from most of this radiation. A generation ship would have no such protection. Shielding helps, but perfect shielding is impossible without adding so much mass that the ship becomes impossibly heavy. Over generations, this radiation would cause mutations. Most mutations are neutral or harmful. The crew's genetic health would slowly deteriorate unless you had sophisticated genetic screening and intervention technologies, essentially playing evolution by carefully selecting which individuals reproduce. Speaking of cosmic radiation, I actually made a video exploring some of the hidden dangers lurking in our own cosmic neighborhood. If you're interested in learning about the terrifying reality of the Kuiper Belt and the threats it poses, check it out after this one. The link is in the description. Now let's talk about something that makes this whole situation even more mind-bending: time dilation. Einstein's theory of special relativity tells us that time passes differently for objects moving at different speeds. The faster you move relative to someone else, the slower time passes for you compared to them. This effect is negligible at everyday speeds, but as you approach the speed of light, it becomes dramatic. Imagine a spacecraft accelerating at 1 Earth gravity, 9.81 meters per second squared. This would be ideal because the crew would experience comfortable artificial gravity throughout the journey. If you could maintain that acceleration continuously, something that would require truly staggering amounts of energy, you would approach relativistic speeds within a year or so of ship time. And here's where things get strange. From the perspective of people on Earth, your journey to a star 10 light-years away might take 11 years or more. But from your perspective aboard the accelerating spacecraft, thanks to time dilation, the journey might feel considerably shorter. This sounds like a solution, doesn't it? Just go really fast, and time dilation will make the trip manageable for the crew. But there are enormous problems with this approach. First, maintaining one gravity of acceleration for years requires fuel and energy that we simply cannot produce with any known technology. Remember the rocket equation, the fuel requirements for sustained high acceleration are beyond absurd. Second, you have to decelerate at the other end, so you'd need to flip the spacecraft halfway through and burn even more fuel to slow down. The total energy budget becomes so enormous that it might require converting significant fractions of planetary masses into pure energy. And third, even if you somehow solve the energy problem, time dilation creates a tragic disconnect. Let's say you embark on a journey to a star 20 light-years away. You accelerate at 1 gravity, flip halfway, and decelerate at 1 gravity. From your perspective aboard the ship, thanks to time dilation, the journey might take only 10 years of subjective time. You'd age only 10 years. But when you arrived, 40 years or more would have passed on Earth. Everyone you knew would be 40 years older. Some would be dead. The world you left would have changed beyond recognition. Technology would have advanced, culture would have shifted. You'd be a time traveler arriving in a future you never experienced. And if you wanted to come back, the same thing happens in reverse. By the time you return to Earth, everyone from your original time would likely be gone. You might have aged only 20 years subjectively, but Earth would be 80 or 100 years older. You'd be a stranger in time, disconnected from your own species by the physics of the universe itself. This isn't just a philosophical problem, it's a practical barrier to any meaningful exploration or colonization. What's the point of sending explorers to the stars if they return to find that civilization has moved on without them? What's the point of establishing colonies if communication delays and time dilation effects mean they immediately begin diverging from Earth, becoming isolated cultures with no real connection to their homeworld? The universe, it seems, is designed to keep intelligent species isolated. The vast distances between stars are bad enough, but when you combine them with the speed of light limit, the energy requirements for relativistic travel, the dangers of interstellar space, and the cruel effects of time dilation, you start to realize that the cosmos has constructed an elaborate prison. We can look at the stars, we can study them, we can dream about them. But actually going there, at least in any way that resembles the science fiction vision of exploring the galaxy, appears to be fundamentally impossible. And we're still not done, because there are even more obstacles we haven't discussed yet. Problems that make the ones we've already covered seem almost trivial by comparison. Let's explore some of the more exotic proposals people have made to circumvent these seemingly insurmountable barriers. Because when faced with impossible problems, human imagination runs wild. Scientists and engineers have proposed ideas that sound like they're straight out of science fiction, and in many cases they might as well be. First, let's talk about antimatter. When a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. This is the most efficient energy conversion process known to physics. Einstein's famous equation E equals mc² tells us that mass can be converted into energy, and matter-antimatter annihilation does exactly that with 100% efficiency. A single gram of antimatter, when annihilated with a gram of regular matter, releases energy equivalent to about 43 kilotons of TNT. That's roughly the same energy as the atomic bomb dropped on Nagasaki. This incredible energy density has led some scientists to propose antimatter propulsion as a solution to interstellar travel. NASA researchers have studied this concept extensively. In theory, you could use antimatter annihilation to heat a propellant and expel it at tremendous velocities, or even use the annihilation products themselves as propellant. The specific impulse, a measure of rocket efficiency, would be orders of magnitude higher than anything chemical rockets could achieve. But here's the problem. We can't make antimatter efficiently. Currently, we produce antimatter in particle accelerators, And the process is spectacularly wasteful. For every unit of energy we get from annihilating antimatter, we have to spend billions of times more energy creating it in the first place. It's like trying to fill your car's gas tank by burning entire forests to distill a single gallon of fuel. The inefficiency is staggering. And even if we somehow developed a way to produce antimatter efficiently, we'd face another nightmarish challenge: storage. Antimatter cannot touch regular matter, or it annihilates instantly. So you need to store it using magnetic or electric fields, suspending individual antiparticles in a perfect vacuum. The containment systems required are complex, energy-intensive, and prone to failure. A single containment breach would result in explosive annihilation. Imagine trying to build a spacecraft fuel tank where the slightest malfunction causes a nuclear-scale explosion. NASA studies suggest that even with optimistic assumptions about future antimatter production and storage technology, we might need 10 grams of antimatter to send a probe to Proxima Centauri. 10 grams doesn't sound like much until you realize that humanity has produced only about 20 nanograms of antimatter in total throughout all of history. That's 20 billionths of a gram. We'd need to increase our production capacity by a factor of 500 million. Some researchers have proposed hybrid systems where tiny amounts of antimatter are used to trigger fusion reactions in a fuel pellet, combining the benefits of both technologies. These antimatter catalyzed fusion concepts could theoretically work with much smaller quantities of antimatter, perhaps mere micrograms instead of grams. But we still haven't achieved controlled fusion, and adding antimatter to the equation doesn't make the engineering any simpler. It's like saying we'll solve world hunger by inventing a magic wand. The magic wand would indeed solve the problem, but we don't have one and don't know how to make one. Now let's venture into even more speculative territory. What about warp drives? This idea was popularized by Star Trek, but it's actually based on real physics, or at least physics that doesn't directly violate the known laws of the universe. In 1994, physicist Miguel Alcubierre published a paper describing a theoretical space-time geometry that would allow faster-than-light travel without actually violating relativity. The Alcubierre drive, as it's now called, works by warping space-time itself. Instead of moving through space, you would compress space-time in front of your ship and expand it behind you. From the perspective of someone outside the warp bubble, you'd be moving faster than light. But from your own perspective inside the bubble, you're not moving at all. Space-time is moving around you. It's an elegant idea that doesn't technically break the light speed barrier because you're not actually traveling through space faster than light. You're manipulating space itself. The problem is that creating this warp bubble would require something called exotic matter, which has negative energy density. And no, this isn't antimatter. Exotic matter would need to have properties that we've never observed and aren't even sure can exist. The amount of exotic matter required in early calculations was absurd, equivalent to the total mass energy of Jupiter or more. Later refinements brought that number down, but even the most optimistic estimates require amounts of exotic matter we have no idea how to produce. Moreover, even if you had the exotic matter, there are additional problems. Research has shown that an observer inside an Alcubierre warp bubble couldn't actually control it. You can't turn it on or off from inside because causality breaks down at the bubble boundary. It would have to be created externally, and you'd essentially be a passenger with no way to start, stop, or steer. Additionally, recent studies have revealed that these warp drive spacetimes might create closed time-like curves, which are paths through spacetime that loop back on themselves, potentially violating causality and creating time travel paradoxes. And there's another devastating problem with the Alcubierre drive that researchers discovered in the years following its proposal. As the warp bubble moves through space, it would accumulate particles and radiation at its leading edge. When you finally shut down the warp drive and the bubble collapses, all of that accumulated radiation would be released in a catastrophic burst, potentially destroying your destination before you even arrived. Imagine traveling to another star system only to inadvertently sterilize it with a lethal blast of high-energy radiation the moment you drop out of warp. Not exactly ideal for exploration or colonization, wormholes represent another science fiction staple that occasionally gets serious scientific consideration. The idea is simple. Instead of traveling the long way around through normal space, you could take a shortcut through a tunnel in space-time connecting two distant points, fold a piece of paper in half, and poke a hole through both layers. That's the basic concept. General relativity does allow for wormhole solutions. They're mathematically valid geometries within Einstein's equations. But, and this is a massive but, they also require exotic matter with negative energy density to remain open. Without it, a wormhole would collapse faster than anything could pass through it. And even if you could somehow stabilize a wormhole with exotic matter, you'd face the challenge of finding or creating one in the first place. Naturally occurring wormholes, if they exist at all, would likely be microscopic, forming and collapsing at quantum scales far too small to be useful. Some physicists have speculated about advanced civilizations potentially engineering wormholes, keeping them open with exotic matter, and using them as a transportation network across the galaxy. It's a beautiful idea, but it requires not only exotic matter, which we don't know how to produce, but also the ability to manipulate space-time at scales that dwarf our current engineering capabilities by unimaginable margins. We're talking about a level of technology so far beyond ours that it might as well be magic. And the energy requirements, potentially equivalent to the output of stars, if not entire galaxies. Let me put this in perspective. Every exotic propulsion system we've discussed, from antimatter to warp drives to wormholes, requires us to solve problems that currently seem impossible. And I don't mean impossible in the way that powered flight seemed impossible to people in the 1800s. I mean impossible in the way that violating the laws of thermodynamics is impossible. These aren't engineering challenges, they're challenges that require new physics, new discoveries that fundamentally change our understanding of how the universe works. Now, some people hear this and say, well, we didn't know about quantum mechanics or relativity 150 years ago. Maybe we'll discover new physics that makes interstellar travel possible. And yes, it's true that our understanding of physics has evolved dramatically. But here's the crucial point. Every new discovery has made the universe seem more constrained, not less. Relativity didn't give us faster-than-light travel, it told us why we can't have it. Quantum mechanics didn't give us free energy, it imposed fundamental limits on what we can know and do at small scales. Thermodynamics gave us laws that cannot be broken, not loopholes to exploit. The history of physics is not a story of discovering that anything is possible. It's a story of discovering the rules that limit what's possible, and those rules have held up extraordinarily well under intense scrutiny. The speed of light limit has been tested in countless experiments, from particle accelerators to astronomical observations, and it has never been violated, not once, not even a little bit. The universe enforces its laws with absolute rigidity. There's also a philosophical argument worth considering. If interstellar travel were easy, or even just possible with sufficient technology, where is everybody? This is known as the Fermi paradox. Our galaxy is billions of years old. It contains hundreds of billions of stars. If intelligent life arose elsewhere, and if interstellar travel were achievable, we should expect to see evidence of it. We should see self-replicating probes spreading throughout the galaxy, or megastructures harvesting stellar energy, or radio signals, or something. The silence is deafening. One possible explanation for the Fermi paradox is that we're alone, that intelligent life is extraordinarily rare. But another, equally plausible explanation is that interstellar travel is simply too difficult. Perhaps every intelligent species that arises eventually confronts the same brutal mathematics we're facing. They look up at the stars, they do the calculations, and they realize that the galaxy is effectively unreachable. They might explore their own solar system thoroughly. They might send robotic probes on multi-millennium journeys to nearby stars, but they never become a galaxy-spanning civilization because the physics won't allow it. This is a somber realization. We are, in all likelihood, confined to our solar system for the foreseeable future, and possibly forever. Not because we lack the will or the imagination, but because the universe has drawn boundaries that we cannot cross. Our sun will eventually die billions of years from now, and unless we've somehow transcended our physical limitations in ways we cannot currently imagine, humanity will die with it. We are cosmically isolated, intelligent beings trapped on a small world, able to observe the vast universe but never to truly explore it. But here's where things get interesting, because I haven't told you everything yet. There are aspects of this problem we haven't discussed, subtle implications that make the situation even more complicated than it appears. The obstacles we've covered so far are formidable, but they're not the end of the story. So far, we've discussed the physical barriers, the vast distances, the energy requirements, the limitations of known propulsion systems. But let's assume, just for a moment, that we somehow solve those problems. Let's imagine we develop a propulsion system that can accelerate a spacecraft to 10% the speed of light, which would get us to Proxima Centauri in about 40 years. This is wildly optimistic given our current technology, but let's grant ourselves this miracle. Would we be ready to go? Would humans finally be on their way to the stars? Not even close. Because now we encounter an entirely different category of problems, ones that have nothing to do with propulsion and everything to do with biology, psychology, and the fundamental limitations of trying to keep fragile human beings alive in the most hostile environment imaginable for decades or centuries at a time. Let's start with radiation. Space is flooded with it. Cosmic rays, high-energy particles, traveling at nearly the speed of light, constantly bombard everything in the void. Some of these particles come from our own sun during solar flares. Others arrive from distant supernovae, some from sources so far away that the particles have been traveling for millions of years before they happen to intersect with your spacecraft. When you're on Earth, you don't notice this cosmic bombardment because our planet's magnetic field deflects most charged particles, and our thick atmosphere absorbs what gets through. Even the astronauts on the International Space Station, orbiting just 400 kilometers above Earth's surface, still receive significant protection from our magnetosphere. But in deep space, there is no protection. Every atom in your spacecraft and every cell in your body is a target. When a high-energy cosmic ray strikes your DNA, it can cause mutations, damage cellular machinery, and increase cancer risk. Long-duration exposure leads to cataracts, cardiovascular damage, and neurological problems. Studies of astronauts who spent extended time on the ISS show measurable cognitive decline and vision problems, and that's with Earth's partial protection and missions lasting months, not decades. The solution seems simple: shielding. Just surround your spacecraft with enough material to absorb the radiation, right? Unfortunately, the physics works against us again. Traditional shielding materials like lead are effective against some types of radiation, but they're actually counterproductive against high-energy cosmic rays. When these particles strike heavy nuclei, they can fragment and create secondary radiation showers that are sometimes worse than the original particle. This is called spallation, and it means that making your shield thicker doesn't necessarily make you safer. The most effective shielding is actually hydrogen-rich materials like water or polyethylene, because light elements don't fragment as severely when struck by cosmic rays. But here's the problem. To achieve meaningful protection, you need meters of shielding in all directions. Water is heavy. A layer of water 1 meter thick surrounding a modest habitat module would add hundreds of tons to your spacecraft mass. Remember our discussion about the rocket equation? Every kilogram of shielding multiplies the amount of fuel you need exponentially. You quickly reach a point where the shielding mass makes the mission impractical. Some researchers have proposed using the spacecraft's fuel and water supply as radiation shielding, positioning these materials around the crew habitat to serve dual purposes. Others have suggested magnetic shielding, creating an artificial magnetosphere around the spacecraft to deflect charged particles, just like Earth's magnetic field does. But generating a magnetic field strong enough to provide meaningful protection requires enormous amounts of power, and the field itself can create other problems, potentially interfering with electronic systems and instruments. And radiation is just the beginning. Let's talk about food. Humans need to eat roughly 2,000 calories per day per person. For a 40-year journey to Proxima Centauri, a crew of just 10 people would need approximately 292 million calories total. Even with the most calorie-dense foods, you're looking at hundreds of tons of provisions. And that's assuming nothing spoils, nothing degrades, and storage containers remain perfectly intact for 4 decades. The obvious solution is a closed-loop life support system, something like a miniature biosphere. You grow your food on board using hydroponics or aeroponics, recycle your waste, regenerate your air and water. It sounds elegant, and it's a technology we've been developing for decades. NASA and other space agencies have conducted numerous experiments with closed-loop systems. But here's what those experiments have consistently shown. Maintaining a stable closed-loop ecosystem is extraordinarily difficult. The ISS recycles about 93% of its water, which sounds impressive, until you realize that the remaining 7% has to be resupplied from Earth. On an interstellar voyage, there is no resupply. Every percentage point of inefficiency compounds over time. Lose 7% of your water per year, and in 15 years, you've lost all of it. You might say, well, just make the system more efficient. But ecological systems are complex, non-linear, and prone to cascade failures. A slight imbalance in one component can ripple through the entire system, causing crop failures, oxygen depletion, or toxic accumulations of waste products. Biosphere 2, an Earth-based experiment in the 1990s, attempted to create a completely sealed ecosystem supporting 8 people for 2 years. It failed. Oxygen levels dropped unexpectedly due to microbial activity in the soil. Carbon dioxide levels fluctuated wildly. 19 of 25 vertebrate species went extinct. Most insect species died off except for cockroaches and crazy ants, which thrived and overran the facility. The crew members lost dangerous amounts of weight due to crop failures and eventually required outside intervention. And this was on Earth, with gravity, with sunlight, with the ability to open the doors if something went catastrophically wrong. Now imagine that same system in space where opening the doors means death, and the nearest help is light years away. Even if you solve the food and water problems, you still have to deal with mechanical failures. Every system on your spacecraft will eventually break down, seals will degrade, electronics will fail due to radiation damage or simple wear and tear. Pumps, fans, filters, all will require maintenance and eventually replacement. You'll need spare parts, tools, and crew members with the skills to repair or fabricate new components. But there's a limit to how many spares you can carry, and some components are too complex to manufacture with onboard facilities. This is where mission duration becomes critical. A 6-month journey to Mars is manageable because you can over-engineer your systems and carry enough redundancy to survive that time frame. But a 40-year journey, a century? The probability of catastrophic system failure approaches certainty. It's not a matter of if something critical will break, but when and whether the crew can fix it before it kills everyone. And then there's the human factor. Psychology and sociology become as important as engineering. You're asking people to spend the prime years of their lives, perhaps their entire lives, confined in a small spacecraft with the same handful of individuals. No privacy, no escape, no way to go outside for a walk or visit family or experience anything new. The landscape outside your window doesn't change. It's just the same black void studded with unmoving stars day after day after decade after decade. The psychological challenges of such confinement are difficult to overstate. We have some data from Antarctic research stations, submarines, and long-duration space missions, and the results are concerning. People in isolated, confined environments experience depression, anxiety, interpersonal conflicts, and cognitive decline. The Russians conducted a simulated Mars mission called Mars 500, where 6 crew members spent 520 days in a sealed facility. By the end, participants showed disrupted sleep patterns, decreased physical activity, and significant psychological stress. 520 days is nowhere near the duration we're talking about for interstellar travel. Social dynamics become a minefield. What happens when crew members develop romantic relationships or conflicts? What if someone becomes mentally unstable? On Earth, or even on a mission to Mars, you can implement interventions, provide counseling, or, in extreme cases, abort the mission and return home. On an interstellar voyage, there is no returning home. You're committed. If someone suffers a psychotic break, your options are limited and grim. You can't evacuate them. You can't bring in a replacement. You have to manage the situation with the resources on board, which might mean sedation, restraint, or in the worst-case scenario, making decisions that no one should ever have to make. Then consider reproduction and aging. If your journey takes longer than a human lifespan, which many interstellar missions would, you need a multi-generational approach. The people who start the journey won't be the ones who finish it. Their children or children's children will arrive at the destination. This introduces a host of new problems. How do you maintain genetic diversity with a small, founding population? Inbreeding becomes a serious concern. You need careful genetic management, perhaps genetic screening, embryo selection, or genetic engineering to prevent hereditary diseases from devastating your population. And what about the children born on the spacecraft? They never chose to be there. They'll grow up in an artificial environment, never seeing a horizon, never feeling rain, never breathing unfiltered air. Their entire world is a metal cylinder hurtling through the void. What kind of psychological impact does that have? Will they understand why they're on this journey, or will they resent the decision made by ancestors they never knew? What if they decide they don't want to complete the mission, that they'd rather turn around or divert to a different destination? This raises profound ethical questions. Do we have the right to commit future generations to a mission they didn't agree to? Is it ethical to create a society where people have no choice about their life trajectory, where their existence is solely to serve as a bridge between one generation and the next? Caretakers of a mission they didn't start and won't finish? Some futurists propose sending frozen embryos instead of living colonists, with robotic systems that would gestate and raise the children upon arrival. This solves some problems like reducing life support requirements during transit, but creates others that are arguably worse. Who raises these children? Robots, AI systems? What kind of society emerges from children raised without human parents, without natural social development? You'd essentially be conducting an unprecedented psychological experiment, creating humans with no connection to Earth or human culture, hoping they somehow turn into functional adults capable of building a civilization. Every solution creates new problems. Every problem branches into a dozen more. It's like trying to navigate a maze where every turn reveals additional layers of complexity, and the exit, if it exists at all, keeps receding further into the distance. But wait, there's more we haven't discussed yet. The challenges I've just described assume you're trying to send living humans on the journey. What if we don't? What if we take a completely different approach? So let's consider the alternatives to sending biological humans. If keeping fragile meat-based organisms alive for decades or centuries is so impossibly difficult, why not sidestep the problem entirely? There are several fascinating proposals that attempt to do exactly this, and each reveals different aspects of what we value about space exploration and what it means to be human. The first alternative is robotic exploration. Instead of humans, send sophisticated robots and AI systems to explore other star systems. This approach has enormous advantages. Robots don't need food, water, or air. They don't get bored or depressed. They don't develop cancer from radiation exposure. They can be powered down during the long transit and activated upon arrival. They can tolerate accelerations and decelerations that would pulverize a human body. And if something goes wrong, it's a loss of machinery, not a loss of life. We've already proven this approach works brilliantly within our solar system. The Voyager probes, launched in 1977, are still functioning nearly 50 years later, now over 20 billion kilometers from Earth. The Curiosity and Perseverance rovers have transformed our understanding of Mars. The Cassini spacecraft spent 13 years studying Saturn and its moons, sending back breathtaking data until its controlled destruction in 2017. These missions cost billions of dollars, but they're a fraction of what crewed missions would cost, and they've yielded extraordinary scientific returns. So why not just send probes to Proxima Centauri? In principle, we could. The challenges are still immense. The energy requirements, the communication delays, the need for autonomous decision-making systems sophisticated enough to handle decades of unforeseen circumstances. But these are all solvable engineering problems, not fundamental violations of physics. A robotic mission to the nearest star system is difficult but plausible. In fact, the Breakthrough Starshot initiative I mentioned earlier, with its laser-pushed light sails, is designed to send swarms of tiny probes to Proxima Centauri. They wouldn't slow down or orbit, they'd just fly through the system at 20% light speed, taking measurements and photos during a brief flyby, then transmitting data back to Earth over the next 4 years. This is probably the most realistic path to interstellar exploration we have. Not humans in gleaming starships, but phone-sized probes weighing a few grams each, accelerated by Earth-based lasers, capturing a few hours of data as they zip through an alien star system at 60,000 kilometers per second. It's not romantic, but it's achievable, possibly within this century. But here's the thing, robotic exploration doesn't satisfy the deeper human yearning to actually go there, to set foot on new worlds, to establish a presence beyond our solar system. There's something fundamentally different between sending a camera to take pictures and actually experiencing a place with human eyes, walking on alien soil with human feet. Science fiction has primed us to imagine humans colonizing the galaxy, not robots doing it on our behalf. So people keep searching for ways to get actual humans to the stars, or at least something close to humans. This brings us to the concept of digital consciousness transfer, sometimes called mind uploading. The idea is that if we could map a human brain completely, capturing every neuron and synapse and their connection patterns, we could simulate that brain in software. The simulation would, in theory, have all the memories, personality, and consciousness of the original person. You could then transmit this digital consciousness across space at the speed of light, or store it in a computer system on board a spacecraft, allowing you to travel to the stars without the biological vulnerabilities of a meat body. Upon arrival at the destination, the digital consciousness could inhabit a robotic body or interface with construction equipment to build habitats and infrastructure, or even create new biological bodies using genetic engineering and stored DNA, essentially uploading back into flesh. You'd have all the advantages of robotic space travel, no need for life support during transit, immunity to radiation, the ability to be copied for redundancy, while preserving something arguably human about the mission. This sounds like science fiction, and currently it is, but it's science fiction rooted in some legitimate research. Neuroscientists have made significant progress in mapping neural connections. The entire connectome of a tiny roundworm, C. elegans with its 302 neurons, has been completely mapped. Researchers are working on much larger mapping projects, including attempts to map portions of mouse brains and eventually human brains. We're developing increasingly sophisticated computer simulations of neural networks. So the underlying science isn't pure fantasy, but, and this is a massive but, we have no idea if consciousness can actually be transferred this way. Mapping the structure of a brain is not the same as understanding consciousness. We don't know if consciousness is purely a product of physical brain structure, or if there's something else, some quantum effect or emergent property that can't be captured by simulation. If you create a perfect digital copy of your brain, is it you, or is it a new entity that thinks it's you, while the original you remains trapped in your biological body? This is the ancient philosophical problem of personal identity, dressed up in technological clothing. And even if consciousness transfer works in principle, would the result truly be human in any meaningful sense? A digital consciousness wouldn't experience physical sensation the way we do. Wouldn't feel hunger, exhaustion, the warmth of sunlight, the pain of injury. Its subjective experience would be so radically different that we might question whether it's the same person at all or something new. A post-human intelligence that merely remembers being human. These aren't just philosophical quibbles, they have practical implications for why we'd bother with interstellar travel at all. If we send digital consciousnesses instead of biological humans, and they arrive at a distant world and build a civilization, is that a human civilization? Have humans colonized another star system? Or have we just created digital descendants who will live lives incomprehensible to biological humans back on Earth? Another alternative that attempts to split the difference is suspended animation or cryogenic preservation. Instead of keeping people awake and alive for the entire journey, freeze them or slow their metabolism to a crawl, then revive them upon arrival. This is a staple of science fiction, from Alien to Passengers to Interstellar. If it worked, it would solve many problems at once. No need for decades of food and life support, no psychological strain from years of confinement, no generational ship complications. You'd go to sleep on Earth and wake up at your destination, experiencing the journey as a single night's rest. Unfortunately, cryogenic preservation is far more complicated than science fiction suggests. We can freeze individual cells, embryos, and even some small organisms successfully. Sperm, eggs, and embryos are routinely frozen and thawed for fertility treatments. Some species of frogs and insects can survive being frozen solid, though they're naturally adapted for this with special proteins that prevent ice crystal formation. But freezing an entire human body, particularly a living one with an intact brain, without causing catastrophic damage, we can't do it. The problem is ice. When water freezes, it expands and forms crystals. The ice crystals pierce cell membranes, shredding the delicate structures that keep cells alive. In the brain, where function depends on precise connections between billions of neurons, even minor damage would likely erase memories and personality. Some researchers are exploring vitrification, a process that turns biological tissue into a glass-like solid without ice crystal formation. But this requires replacing much of the body's water with cryoprotectant chemicals that are often toxic, and we have no proven method for reversing the process safely. Current cryonics organizations that offer to freeze people after death are banking on future technology being able to repair the damage and revive the patient. This is speculative at best. You're essentially betting that future civilizations will have technology so advanced they can reverse freezing damage, repair whatever killed you in the first place, and restore your consciousness, despite the fact that current science suggests the brain damage from freezing is likely irreversible. It's not impossible in principle, but it requires technology far beyond anything we can currently envision, perhaps even requiring molecular-scale manipulation with nanorobots or similar speculative tech. Even if suspended animation could work, there's still the matter of reliability. You're trusting automated systems to keep you frozen for decades or centuries, to monitor and maintain cryogenic temperatures without failure, and then to thaw and revive you at precisely the right time. Given our earlier discussion about system reliability over long mission durations, putting your life in the hands of equipment that must function flawlessly for that long is an enormous gamble. Some proposals suggest chemical-induced metabolic hibernation instead of freezing. Some mammals naturally hibernate, slowing their metabolism dramatically to survive months without food. If we could induce a similar state in humans, perhaps through drugs or genetic modification, people could sleep through most of the journey, requiring only minimal life support. This is more plausible than cryonics because it doesn't involve freezing and thawing, but we currently don't know how to induce true hibernation in humans safely, and even hibernating animals aren't completely dormant. They still need some resources, still age, still face risks from system failures. There's also a darker alternative that occasionally appears in serious discussions, sending only genetic material. Not frozen embryos that need to be gestated, but raw DNA. The spacecraft would carry genetic information for humans and various Earth organisms, along with robotic systems capable of synthesizing DNA, creating embryos, gestating them in artificial wombs and raising the resulting children. Upon arrival, the robots would manufacture humans and plants and animals from scratch, seeding a new world with Earth life without ever transporting living organisms across the interstellar void. This approach minimizes the mass that needs to be sent, digital genetic data and robotic equipment rather than living organisms and decades of life support. It sidesteps most of the biological challenges of space travel. And it allows for genetic modifications to be made to adapt the resulting organisms to conditions on the destination world. You could create humans with enhanced radiation resistance, altered metabolisms for different atmospheric compositions, or other modifications that would help them thrive in an alien environment. But again, the ethical problems are staggering. You'd be creating sentient beings who have no parents, no natural social development, no connection to human culture, except what robots can teach them based on programmed databases. It's a massive experiment in artificial social development, and the potential for things to go wrong is enormous. What kind of society would emerge? Would these beings even consider themselves human? Would they value the same things we value, have the same goals, the same ethics? And there's a subtle horror to this approach that's worth acknowledging. You wouldn't be sending humans to the stars. You'd be sending a blueprint for humans, instructions for building people who've never existed, creating new minds and bodies to serve as colonists without their consent. It feels less like exploration and more like manufacturing expendable biological units to fulfill an agenda. The people created this way are tools, not travelers. Every alternative to traditional crewed missions seems to require either technology we don't have and may never develop, or accepting a mission profile that fundamentally changes what we mean by human space exploration. We keep running into the same basic problem from different angles. Human biology is adapted for Earth and nothing else. We're creatures of gravity and atmosphere, of day-night cycles and seasonal variation, of complex ecosystems and social structures. Remove those elements and we struggle. Extend the duration of that removal beyond months into years or decades, and the challenges become nearly insurmountable. But suppose, just for the sake of argument, that we accept all these challenges. Suppose we decide that despite the energy requirements, despite the radiation hazards, despite the psychological toll and the ethical quandaries, we're going to send humans to another star system anyway. We're going to build a generation ship or invent cryogenic suspension, or find some other solution. Consequences be damned. Could we do it? Is there any plausible scenario where humans actually reach another star? The answer is maybe, but only under very specific circumstances, and only if we're willing to accept a mission profile that looks nothing like the Star Trek vision of interstellar travel. Let's imagine the most realistic scenario we can for an actual crewed mission to another star. Not the optimistic science fiction version, but something grounded in what we know about physics, engineering, and human biology. What would it actually take, and what would it look like? First, we'd need to pick our target carefully. Proxima Centauri is the closest star at 4.24 light-years, but proximity isn't everything. Proxima Centauri is a red dwarf, a small, dim, temperamental star that regularly produces massive flares that would bathe any planets in deadly radiation. Its habitable zone planet, Proxima Centauri b, might be tidally locked, meaning one side always faces the star while the other remains in eternal darkness. The temperature differential would create permanent hurricane-force winds, and the stellar flares could strip away any atmosphere the planet once had. It's close, but it might not be hospitable. Other nearby candidates exist. Alpha Centauri A and B are sun-like stars in a binary system, also about 4.37 light-years away. They're more stable than Proxima, and recent observations suggest there might be planets in the habitable zones of both stars. Barnard's star, at 6 light-years, is another red dwarf but appears calmer than Proxima. Tau Ceti, at 11.9 light-years, is a sun-like star with confirmed planets, though we don't yet know if any are truly Earth-like. The James Webb Space Telescope and future observatories will tell us more about the atmospheres and conditions of these worlds, helping us identify which, if any, might actually be suitable for human habitation. Let's assume we find a promising target, a planet around a stable star within 10 light-years, with a breathable atmosphere, liquid water, and no obvious deal-breakers like extreme radiation or toxic chemistry. Now we need to design our mission. Given all the constraints we've discussed, what's the most plausible approach? The spacecraft would need to be massive, almost certainly the largest object humans have ever constructed. We're talking about a vessel multiple kilometers in length, possibly kilometers in diameter, if it rotates to provide artificial gravity through centrifugal force. It would need to be assembled in space, probably in orbit around the Moon, or at one of Earth's Lagrange points, because launching something that massive from Earth's surface would be impossible. The construction would take decades, perhaps a century, requiring thousands of launches to deliver materials and components, along with armies of workers and construction robots operating in zero gravity. The propulsion system would likely be nuclear, either fission or fusion if we can make it work. Chemical rockets are simply too inefficient. Solar sails might provide some acceleration in the early stages while still relatively close to the Sun, but can't carry you all the way at useful speeds. Nuclear pulse propulsion, the concept behind Project Orion, where you detonate nuclear explosions behind your spacecraft and ride the shockwave, could theoretically reach 5 to 10% of light speed, making the journey to a star 10 light-years away take between 1 and 2 centuries. It's a brutal, inelegant solution, but it might be the only one that works with physics we actually understand. The spacecraft structure would need to be layered. The outermost shell would be a Whipple shield or something similar, spaced layers of material designed to vaporize and disperse micrometeorites before they can penetrate to the inhabited areas. Remember, at even a few percent of light speed, a grain of sand carries the kinetic energy of a bullet. Beneath the Whipple shield would be radiation shielding, probably meters of water or hydrogen-rich materials. Then the structural framework, which would need to be incredibly strong to withstand the stresses of acceleration and the centrifugal forces if the ship rotates. Inside this protective cocoon would be the habitat modules, probably arranged in rings or cylinders to create artificial gravity through rotation. You'd want at least 0.3 Earth gravities to prevent severe bone and muscle loss, though 0.5 to 0.7 would be better. This means the habitat sections need to be large and spinning at specific rates to achieve the right centrifugal acceleration. Too small and the rotation rate becomes nauseating due to Coriolis effects. Too large and the structural requirements become prohibitive. The habitats would need to be self-sustaining ecosystems, closed-loop life support with redundancy built into every system, multiple hydroponic farms growing fast-cycling crops like lettuce, tomatoes, and dwarf wheat. Algae tanks for additional oxygen production and protein synthesis, perhaps even small livestock, chickens or fish, though the resource costs of maintaining animals might be prohibitive. Every drop of water would be recycled, every breath of air scrubbed and regenerated, every scrap of organic waste composted and returned to the growing systems. The failure of any major component could cascade into disaster, so you'd need duplicate and triplicate systems, automated monitoring, and a crew trained in agricultural science, environmental engineering, and emergency life support repairs. The crew size is critical. Too small and you lack the genetic diversity and skill variety needed for a multi-generational mission. Too large and the resource requirements become impossible. Based on studies like those conducted by Frederick Marat, you'd probably need a starting population of at least 150 to 200 people to maintain genetic health over multiple generations, provide enough specialists to keep the ship running, and buffer against inevitable losses from accidents, disease, and random chance. These people would need to be carefully selected not just for physical health and skills, but for psychological resilience, social compatibility, and genetic diversity. And here's where the mission profile becomes truly sobering. For a journey lasting a century or more at a significant fraction of light speed, you're committing multiple generations to life aboard the ship. The original crew, let's call them Generation Zero, volunteers for the mission knowing they'll never see the destination. They'll spend their entire lives aboard the ship, having children, raising them, growing old, and dying in the void between stars. Their children, Generation 1, and their children's children, Generation 2 or 3, will be the ones who finally arrive. None of them chose this life. They were born into it, their entire existence defined by a mission decision made before they existed. To make this work, you'd need strict social engineering. Reproduction would have to be carefully managed to maintain population size and genetic diversity. Births would need to be approved and scheduled. Mate selection might be influenced or controlled to optimize genetic outcomes. Education would be standardized and focused on skills necessary for ship maintenance and mission completion. Individual freedoms would necessarily be curtailed because the survival of the entire population depends on everyone fulfilling their roles. It would be less like a democratic society and more like a highly regimented organization, perhaps something between a monastery, a research station, and a military vessel. What kind of culture would develop in such an environment? Would people maintain connection to Earth, following news and history transmitted from billions of kilometers away? Or would they develop their own identity separate from their homeworld? How would they handle the knowledge that everyone they see in transmissions from Earth is long dead by the time the messages arrive, and that by the time their own messages reach Earth, generations will have passed? Communication becomes increasingly strained as distance grows. At 10 light-years away, a message to Earth takes 10 years to arrive, and any response takes another 10 years to come back. A 20-year round trip for communication means you can't ask for advice or help. Every decision must be made locally, autonomously. The ship and its population become fundamentally isolated, a tiny, independent world with no possibility of rescue or resupply. And then there's the arrival. After a century or more of travel, the ship approaches the destination star system. This is perhaps the most dangerous phase of the entire mission. Remember, you need to decelerate. If you've been accelerating to 5 or 10% light speed, you need to shed all that velocity or you'll blow right past your target. That means firing your engines in reverse for years or decades, consuming whatever fuel reserves you've carefully hoarded. If something goes wrong with the engines during deceleration, if you can't slow down enough, the entire mission fails. You might not have enough fuel to return to cruising speed, leaving you drifting through the destination system without the ability to brake or accelerate, slowly freezing as your power systems die. Assuming deceleration works, you enter orbit around your target planet. Now comes the moment of truth. Does the planet actually support human life? Is the atmosphere breathable? Are there deadly pathogens or toxic compounds that weren't detectable from Earth? Is the gravity tolerable? Are there resources, water, minerals, energy sources sufficient to sustain a colony? You've spent a century traveling to this destination based on observations made from light years away, which means you're seeing the planet as it was a century ago. Anything could have changed in the intervening time. If the planet is unsuitable, your options are grim. You don't have the resources to travel to another star. You can't return to Earth. That would take another century, and you don't have the fuel. You're trapped in orbit around an uninhabitable world, and your only choice is to try to survive on the ship indefinitely, perhaps mining asteroids or moons in the system for resources, becoming a permanent, space-dwelling civilization that never intended to be one. This is the nightmare scenario that keeps mission planners awake at night. A one-way trip to nowhere, discovering too late that you've committed multiple generations to a dead end. But let's assume the best case. The planet is habitable, or close enough. Now you face the challenge of actually colonizing it, transitioning from a space-dwelling population to a planetary one. Your people have lived for generations in artificial gravity, recycled air, and controlled environments. They're about to set foot on a world with real weather, natural ecosystems, unpredictable hazards. It's an alien environment in the most literal sense, and humans evolved for Earth, not this place. The gravity might be higher or lower than Earth standard. If it's significantly higher, people raised in the ship's lower artificial gravity might struggle with the increased weight, experiencing joint problems, cardiovascular stress, and exhaustion from simple movement. If it's lower, they might adapt more easily, but bone and muscle loss would accelerate unless they maintain rigorous exercise regimens. The atmosphere might be breathable, but with different ratios of oxygen and nitrogen, requiring an adjustment period and potentially causing long-term health effects. Then there are biological concerns. Does the planet have its own ecosystem? If so, Earth biology and alien biology will interact in unpredictable ways. Plants and animals from Earth might thrive or fail catastrophically, depending on soil chemistry, microbial populations, and competition with native life. Alien microorganisms might be harmless to humans, or they might cause novel diseases against which we have no immunity. The colonists would need to conduct extensive testing, probably living in sealed habitats initially, and only gradually expanding into the environment as they understand its dangers. Building infrastructure on the surface would be an enormous undertaking. The ship probably can't land. It was built in space and designed for space. So the colonists would need to use shuttles or landers to ferry people and equipment to the surface, establishing a beachhead and constructing shelters, power systems, and agricultural facilities from scratch. They'd essentially be starting a new Bronze Age, except with some advanced technology and knowledge. But manufacturing complex equipment requires industrial infrastructure that doesn't exist yet. You need refineries to process raw materials, factories to produce tools and components, energy systems to power everything. Building a self-sustaining planetary civilization from nothing would take generations, and during that vulnerable period, any major disaster could wipe out the colony. And even if everything goes perfectly, even if the planet is ideal and the colonization succeeds, what have you accomplished? You've moved a few hundred or thousand humans from one star system to another. You haven't meaningfully expanded humanity's presence in the galaxy. You've created a single, isolated colony that will face all the same resource limitations, social challenges, and eventual stellar death that Earth faces, just in a different location. To truly become a multi-star civilization, you'd need to repeat this process hundreds or thousands of times, sending generation ships to every promising star within reach, creating a network of colonies that might eventually be able to communicate and trade across light-year distances, though the time delays make meaningful interaction nearly impossible. This is the vision that remains plausible within known physics: slow, expensive, dangerous colonization of nearby star systems, each mission taking centuries and representing a colossal investment of resources and human lives. Not the elegant, faster-than-light starships of science fiction, but lumbering generation ships full of people who will never see their destination, crawling across the void at a fraction of light speed, hoping the planet they reach was worth the sacrifice. And here's the uncomfortable truth: even this limited vision might be beyond us. The economic and political will to undertake such missions might never materialize. The resources required are staggering, and the returns are intangible and delayed by centuries. What government or organization invests decades of GDP into a project that won't produce results for 100 years or more? Who signs up to be Generation Zero, knowing they're condemning themselves and their children to life aboard a ship purely so distant descendants can set foot on an alien world? Yet without this commitment, humanity remains confined to one solar system, one planet really, because even colonizing Mars or the moons of Jupiter pales in significance compared to truly leaving our stellar neighborhood. We remain vulnerable to any catastrophe that affects Earth or our Sun. In the longest term, we remain mortal as a species, confined to one small corner of one galaxy, able to see the vast universe but never to touch it. Is this the true barrier? Not physics or engineering, but will? The realization that interstellar travel requires sacrifices we're not willing to make, commitments across generations that our societies aren't structured to support,